Hey, I'm back. Let's talk about linear programming. Not so much about computers. So linear programming is a method for finding minimum or maximum value of some quantity given a set of constraints. Some real-world problems involve multiple linear relationships, and linear programming helps us figure out the best way to solve those problems. Constraints in linear programming they make this system of inequalities, and they give you a feasible region, right? And it contains all the points that satisfy the constraints. The quantity you're trying to maximize, which is usually cost or profit, is represented by an objective function. So we're going to suppose that our objective function is cost equals 2x plus y. We graph that objective function through the different points of the feasible region, and the points that are closest to the origin minimize the objective function, or the lines that are closest to the origin minimize the objective function, and the lines that are furthest from the origin maximize the objective function. So if you want a minimum, you're gonna apply the objective function and evaluate it at the point in the feasibility region that puts the line closest to the origin. If you're trying to get a maximum, you're going to evaluate the objective function for the point that puts the line the furthest away from the origin. Okay, so there is a maximum or minimum value of the linear objective function. If there is one, it occurs at one or more of the vertices of the feasible region. Top notch. That's your secret phrase, top notch. So, what point in the feasible region maximizes the profit p for the objective function p equals 2x plus y? Here are my constraints. So we need to graph those constraints. X is greater than or equal to 0, y is greater than or equal to 0. That just means we're not looking at anything over here. I mean, usually in a real life situation, things that you're measuring don't go negative. So we just look in quadrant 1. X plus 2y is greater than or equal to 5. That's this guy right here. No, it's not. It's this guy right here. X plus 2y is greater than or equal, less than or equal to 5. And then x minus y is greater than or equal to 2. Less than or equal to 2. Man, I can't even talk today. So, this area in here is your feasible region. So the first step is always to graph the inequalities. The second step is form the feasible region. The boundaries all intersect, and it's whatever's inside. Then you want to find the coordinates of each vertex. And if they're not easy to see, you can always just solve the system of equations that are represented by these lines. They're inequalities when they're listed as constraints, but if you put an equal sign on these two and then solve them, you'll get the point where those two intersect. So we got 0, 0, we've got 0, 2.5, we've got 3, 1, and 2, 0. So those are the coordinates of the vertex of our feasible region. Once you know the coordinates of the vertices, the next step is to evaluate the objective function at each vertex. So our objective function was 2x plus y, p equals 2x plus y. So at 0, 0, it's going to be 2 times 0 plus 0 equals 0. It generally means if you don't sell anything and you don't sell anything, you make nothing. If we plug in for 0, 2.5, we get 2 times 0 plus 2.5 is 2.5. If we plug in for 3, 1, 2 times 3 plus 1 is 7. If we plug in for 2, 0, 2 times 2 plus 0 is 4. And we get our maximum value at the point 3, 1, and our maximum value is 7. So p has a maximum value of 7 when x equals 3 and y equals 1. So the correct choice back here on multiple choice land was C. Alright, so let's see if you got it. Use the constraints in problem 1 with this objective function. What values of x and y maximize p? So we're going to use the same vertices, 0, 0, 0, 2.5, 3, 1, and 2, 0. And we're plugging them into p equals x plus 3y. So for 0, 0, p equals 0 plus 3 times 0, which is 0. For 0, 2.5, p equals 0 plus 3 times 2.5, which is 3 times 2.5 is 7.5. At 3, 1, p equals 3 plus 3 times 1, which is 6. And for 2, 0, p equals 2 plus 3 times 0, which is 2. So our maximum is 7.5 at the point 0, 2.5. So depending on what the objective function is, it might be closer to the origin at a different point than a different objective function might be. So it's not going to be the same point every time. So given your objective function, you need to check all the points to see which one gives you the maximum. Alright, so real world. Use linear programming to maximize profit. You are making some t-shirts and sweatshirts to sell at the Blues Festival. Here are your constraints. You have at most 20 hours to make the shirts. You want to spend no more than $600. So at most 20 hours, no more than $600. You want to have at least 50 items to sell. How many shirts and how many sweatshirts should you make to maximize your profit? And how much would that profit be? Here's some information here. It takes 10 minutes to make a t-shirt. Supplies cost $4. The profit is $6. It takes 30 minutes to make a sweatshirt. Supplies cost $20 and the profit is $20. The first thing we need to do is organize all this. This is a lot of information. We need to organize it into a table so that we can kind of look at it all at once. Here's our table. We got t-shirts and sweatshirts. We're going to call t-shirts X and sweatshirts Y. We know that it takes time to make these shirts, right? 10 minutes to make a t-shirt, so 10 minutes times the number of shirts. Sweatshirts is 30 minutes each, so 30 minutes times the number of sweatshirts. And that those can add up to 1,200. What does the 1,200 mean? Well, you got 20 hours, and 20 hours times 60 minutes in each hour is 1,200 minutes. And so when you add these together, they need to be less than or equal to 1,200 because at most 20 hours. So the number of shirts you want to be at least 50. So X plus Y wants to be greater than or equal to 50. The cost of the shirts cost $4 each, so $4 times the number of shirts, plus the sweatshirts cost $20 to make, so $20 times the number of sweatshirts, and then we want that to be no more than $600, so that's less than or equal to $600. The profit, this is our objective function, we make $6 off every t-shirt, so 6x, plus we make $20 off of each sweatshirt. So our objective function is p equals 6x plus 20y. So write the constraints and the objective function. Those come to us pretty easily off of this table that we made. 10x plus 30y is less than or equal to 1,200. X plus y is greater than or equal to 50. 4x plus 20y is less than or equal to 600. X is greater than or equal to 0. Y is greater than or equal to 0 because we're not going to sell negative shirts or negative sweatshirts. And the objective function is p equals 20x or 6x plus 20y. Alright, so we got lots of information now. We did all this thinking and all this talking to get our constraints and our objective function. So our first step is to graph the constraints to form the feasible region. And this graph was done for us, but in an example I'll show you how to do that. Next is to find each vertex. So we got 50, 0 here. We've got 120, 0 here. This one is 75, 15. And this one is 25, 25. Next, we evaluate our objective function, which is profit, for each one of these coordinates, for each one of these vertices. And we end up getting our maximum at the point 75, 15, which is C. And our maximum profit is 750. So now we know that we would maximize our profits if we sell 75 t-shirts and 15 sweatshirts. So that'll help us plan. We'll make 75 t-shirts and 15 sweatshirts, and that will make it most likely that we'll get the biggest profits. So, what if you took 20 minutes to make a sweatshirt? If you got faster at sweatshirts, then how would that change your plans? Well, we still have the same constraints, almost. Instead of being 30 minutes for a sweatshirt, it would be 20 minutes for a sweatshirt, which would change this. So that is going to change our graph. So here is a graph of our old functions, our old constraints. Just to make sure, see if we have our points line up where they were before. And they do. So this is our old feasible region. Let's see what happens when we change this to 20. Now we have a new point here, 110. So our points are 25, 25, 50, 0, 110, and 120, 0. Alright, so let's test these points. We still got the same profit function. $6 for shirts plus $20 for sweatshirts. This is the one I'm most interested in because that's the one that changed. In fact, I already know what the profit would be for all of those because I did them just a minute ago. So this is the one I'm really interested in. So 6 times 100 plus 20 times 10 is 600 plus 200, which is 800, which is higher than our max on our last problem. So that changes. So if we get better at sweatshirts, we can make them in 20 minutes. Now we want to make 100 t-shirts and 10 sweatshirts, which might seem a little weird because our old profit was 75 t-shirts and 15 sweatshirts. But I think what happened is we freed up so much time with the sweatshirts that we could make more money off of the t-shirts by making more t-shirts. So this is our optimum. Sometimes it doesn't work out the way you think, right? Getting better at sweatshirts actually just helped us sell more t-shirts. So math is amazing. It's wonderful. It will help you make money. And that's the end. I'll talk to you later. See you soon. Those are soon and later. Hey, cool. Opposites. Bye.